Hi class, in this last part of the first section of Chapter 15 we're going to now talk about masses of stars. So we've already talked about how do we measure brightnesses of stars, the true brightness of a star, the luminosity, versus the apparent brightness, how far or how bright it appears to be. And to compare those two we need to know distance. So we figured out how to do that. And then we talked about temperature. And so for temperature we need to look at the light itself very carefully and look at the spectrum and the different colors that the star gives off, and perhaps look at the colors that are absorbed by certain gases or atoms, molecules and such, and that tells us a good deal about temperature. But now what about the masses of the stars? How massive are the stars? To do that, we need to have the star interacting with something. The star has to be pushing and pulling on something else by the force of gravity so we can measure its mass. So we're going to talk about binary star systems, stars that are orbiting other stars. This is an example, the star Mizar. If you look in the Big Dipper, the star Mizar, and there's also the star above it is Alcor. Those are two binary stars. They're orbiting each other, actually, a pretty good distance apart. But if you zoomed in on both of them, in particular, if you zoomed in on Mizar, you actually see that Mizar, which looks like one star to us, is actually two stars orbiting each other. But if you zoom in even further, each of those two is two stars orbiting each other. So this is actually Mizar, the star we see in the Big Dipper, is actually four stars orbiting. These two guys are orbiting around each other, these two are orbiting around each other, and these pairs are orbiting around each other. And then that whole system of four stars, the Mizar system, is actually orbiting Alcor. And Alcor is actually a binary as well. So there's actually six stars here orbiting each other in a fairly complicated way. To your naked eye, you might only see these two, but if you looked in a telescope at Mizar in particular, you would see these two. To see that there's actually four, you would need a more powerful telescope than a typical backyard telescope. So to measure the mass of stars, we need them to be interacting with something. We can go back then to Kepler's laws and talk about how the period of orbit of one body orbiting another body is related to the size of the orbit. The average distance between the bodies. We use that law to determine the masses of the two objects. But we need to know the period, we need to know the amount of time it takes for the orbit to occur, and we need to know the distance between the stars. So one of those things is easy to get, the other thing is a bit more difficult to get. So the different types of binary systems that we'll talk about are visual binaries. Visual binaries, you can actually see through a telescope that there are two stars there. And over time, you can actually watch them move around each other, and you can easily measure then the amount of time it takes for them to go around. A spectroscopic binary is a binary that you can't necessarily see as two separate stars, but you can tell that things are moving because of the changes in the spectrum. And then an eclipsing binary is when one star passes in front of the other and vice versa. They each pass in front of the other on each half orbit. And what happens there is you get the brightness of the system going down and then going back up as one star eclipses the other star. So these different binary systems give us different information. A visual binary, you can see it, and so you can maybe most easily determine the period, the amount of time it takes. Spectroscopic binary, you can't necessarily see there's two stars, but you can infer that there must be two by changes in the spectrum. So we'll talk about the limitations, what you can know about these different stars and these different systems, and what kind of limitations there are in terms of determining the mass. One thing though that's important to note is that, let's say you have an eclipsing binary. What that means is that one star is passing in front of the other again. But that eclipsing binary is also a spectroscopic binary. In fact, any binary system is a spectroscopic binary system, with one exception, and that would be if the plane of the orbit of the two stars is perpendicular to your line of sight. So to be a spectroscopic binary, as the stars orbit, they are coming towards you and going away from you as they orbit around, and that coming away or going toward kind of changes as time goes on. And so in the spectrum with the Doppler effect, you can see the changes in the spectrum. So eclipsing binaries are also spectroscopic binaries. That's definitely true. But a binary system where the orbital plane is perpendicular to your line of sight would not be a spectroscopic binary, nor of course would it be an eclipsing binary. And if it's not a visual binary, if you can't actually see there's two stars, you might not even notice that it is a binary system to begin with. So let's go through these different types. In a visual binary, here's an example of a picture taken in the year 1900, for example, of star A and star B. And over time, you can see how the stars are changing position. And if you look for some kind of repetition here, if you compare the picture of 1900 to the picture of 1950, they look nearly the same, almost identical. And so the period, the amount of time it takes for the orbit to go around once, the stars to orbit each other once, is about 50 years. And if you took the pictures really carefully and you took the pictures, let's say every month, you could kind of really pinpoint the orbital period of those two visual binaries. Spectroscopic binaries, though, you might not be able to see the two individual stars, but what you see is that, in this case, we've got like a hot bluish star going around a bigger red star. And if this is the Earth, this is our telescope, during one part of the orbit, this smaller blue star is traveling toward the Earth. Right? And we know from the Doppler effect that light that's being given off by an object traveling toward us has the various spectral features shifted toward the blue part of the spectrum. Those features are blue shifted. A color that would normally be a particular wavelength of red has a wavelength a little bit shorter, a little bit, maybe it's still red, but it's a little bit shorter, it's a little bit more toward the blue part of the spectrum. So these four absorption colors we see here, red, bluish, greenish, kind of teal, purples, these are hydrogen absorption colors. And so if the star was just sitting still, these absorptions would occur in a certain place at a certain wavelength. But while the star is moving toward us, those absorptions get shifted a little bit to the blue part of the spectrum, to the right. And what we notice over time is that as the star orbits around and at one point is traveling away from us, those same spectral lines, the whole pattern in fact, shifts to the left. It shifts toward the red part of the spectrum. So it goes from being blue shifted while the star is traveling toward us to being red shifted while the star is traveling away from us. And the cycle continues. It just keeps repeating itself over and over and over again. So here's an example in your one of the interactive figures. Here's an example of star A and star B going around each other, and really both stars are moving. In this case, we see the spectral lines. This spectrum is reversed from what we saw in the PowerPoint, but we still see these four spectral lines, the reddish one, the bluish green, and the purples, shifting back and forth as the star goes away from us and toward us. The Earth is over here, so in this direction, the light would be going toward the Earth. So right now, star B is traveling away. Right now, star B is traveling toward the Earth, and so on. And you can see that over time, the spectral absorption features shift back and forth. And you might say, well, what about star A? Star A gives off light too. Well, yeah, it does, and you might be able to see the spectrum of star A, or if star A is too dim, you just might see the spectrum of star B. This little video is an example of a system where both stars are moving and you can see both spectral features. And you can see that as, oops, see if I can play that again. Here we go. As one star is orbiting the other, both stars are actually orbiting, and you can see there's a reference line. Let me play that again. There's a reference line that sits still, and you can see there's two absorption lines labeled A and B that go back and forth around that sort of reference line. So if both stars are bright enough for you to see, you'll see these patterns of colors shifting to the right and left at the same time and then coming back and sort of going in opposite directions, kind of continually shifting back and forth. So the amount of the shift, the sort of the maximum shift that you see in the spectrum, gives you the velocity of the stars toward or away from you. But the problem with the spectroscopic binaries is you don't really know how the orbit is inclined. You don't really know if the stars are orbiting edge on to the Earth. So like in this system, if the orbital plane was the screen here and the Earth was over here somewhere, then when the star B is moving toward the Earth down here, it's really exactly moving toward the Earth. And it's moving directly away from the Earth up here. But if the orbital plane of the system is tilted in any way, then when the star looks like it's orbiting toward the Earth, it might be kind of orbiting toward the Earth but upward a little bit or downward a little bit. And so you only get, with the Doppler effect, you can only measure a component of the velocity toward the Earth. You might not be able to measure the full speed, the full velocity of the star. So there is a limitation on the spectroscopic method as to what you can actually know. So that's the spectroscopic binary system. And then in the eclipsing binary system, in this, what happens here is you've got one star orbiting another again, but the orbit is edge on, nearly edge on. It might be perfectly edge on or mostly edge on, maybe not exactly edge on, but it could be a variety of possibilities. But if one star goes in front of the other, or while they're not in front of each other, what you see is you see the total light from both stars. So you see a certain intensity, a certain brightness. So you have a graph of brightness, apparent brightness as a function of time. And so there's a certain brightness that star A gives you, plus a certain brightness that star B gives you. When star B goes in front of star A, we still see all the light from star B, but some of the light from star A is blocked. So we see less light from star A. The total light we see has gone down. And suppose star B is a brighter star. It has a higher temperature. So every square meter of star B would be giving off more energy. So if star B goes behind star A, we lose all of star B's light, but we see all of star A, and in this case we see an even bigger drop in the total brightness of the system. And this pattern would repeat over and over and over again. And so we'd be able to measure the amount of time it takes for the system to go from one configuration back to that same configuration. We'd be able to measure the period very easily by measuring the time between these sort of drops in brightness. And so we can measure the period very well with these eclipsing binaries. We can measure the period really well with the spectroscopic binaries as well. We just look for this pattern shifting back and forth and measure how much time it takes for it to make one complete back and forth motion. So we can measure period very easily, the amount of time for the orbits very easily with any of these methods. So what do we do with that information? Well, here's Kepler's law from back in a previous chapter. The amount of time it takes for one object to orbit another in a binary system, like a star orbiting another star, or a planet orbiting a star, or even a moon orbiting a planet. That period is equal to 4 pi squared over the gravitational constant times the sum of the two masses. So the two masses get added together down here. And then this is the average distance between them to the third power, the average separation to the third power. So we are trying to solve for the masses. So we can find the period easily through these methods, either of these three methods, looking at the visual binary and taking photographs over time, looking at the spectroscopic binary and looking at the change in the pattern of the spectrum, or looking at the eclipsing binary and looking at the changes in the brightness as it goes up and down and back down and so on, as one star is eclipsing the other. But we also need to find the distance. We need to find the distance between the orbits. And that's hard to do unless you can see the stars more directly. That's a little bit more difficult. For visual systems, it's a bit easier to do. So we have to make some sort of approximations. We can get some information about separation, but maybe not perfect information. So these masses that we calculate always have some uncertainty to them. What we often calculate is some minimum mass that the stars must have. Maybe there's more mass, but it's hard to say exactly. We need two of these three things. If we can find the period, which we can find, all right, we can plug that into the equation. We also need the separation. But we can also think about velocity, because velocity and separation and period are related. If you think about the stars going around in an almost circular orbit, the velocity of the star is the circumference, the distance traveled, divided by the time it takes. So the velocity can be determined through that spectroscopic method by looking at the shift in the wavelengths of light from the Doppler effect. But you can't determine this precisely unless the star's orbit is edge on to you. So all you really can measure with the spectroscopic method, all you can really know for sure is that whatever you're measuring is a minimum on what the velocity is. The velocity could be higher. If the orbit is tilted, then what you're measuring is just a component of the velocity pointing toward you or away from you. And so the actual velocity might be faster. And so you might be able to get a minimum for this, which means you might be able to get a minimum for the radius by incorporating the period into your measured velocity. So all we need are two of these three quantities. For visual binaries, we might be able to directly measure the radius, but for the spectroscopic binaries and the eclipsing binaries, we can measure the velocity. But again, there are some limitations to how well we know that velocity. So in any case, we can get decent ideas, good approximations at least, of the masses of these stars in these binary systems. So when we do that, we find that there are stars out there with huge amounts of mass, 100 times the mass of the Sun. There's also stars out there that have much smaller mass, about 0.08 times the mass of the Sun. So very small mass stars to very large mass stars. M Sun is the mass of the Sun. So one other thing before we wrap this up, the one advantage of the eclipsing binary is that you can also get information about the radius of the stars by timing how long it takes for a star to go in front of another. And thinking about timing and the speed, you can get information about how far a star has to travel from one edge, like the blue star, from one edge of the red star to the other edge of the red star. That gives you information about the radius of the big star, as well as the small star. So with the eclipsing binary system, you can actually get not only distance information between the stars, but also the radius of the stars themselves, at least to a good approximation. So in this first section of Chapter 15, we've learned several things about measuring things about stars. We can talk about the stars' true brightness, how much energy they give off every second. It's called the luminosity. And we get that information by knowing distance and combining that information with apparent brightness. But how do we get distance? We get distance by looking at parallax, by looking at a shift in the star's position as the Earth orbits the Sun. But that doesn't work for all stars. That only works for stars that are fairly close to the Earth, because it's hard to measure those very tiny angular shifts in position of stars. And then we can measure temperatures by looking at the spectrum of light that a star gives off, and looking at what elements, what atoms, what gases, what molecules are present in the spectrum, and understanding how gases give off or absorb certain colors based on their temperature. We can then figure out the temperature of the star. And then finally, we measure masses by applying Kepler's third law, by looking at different binary star systems. And we can find the period pretty easily, the amount of time it takes for the stars to orbit each other pretty easily. But the distance between the stars is a bit trickier. If we can measure the velocity very accurately, then we can get the distance between the stars. But we can't always measure that velocity with 100% precision. There might always be, we just don't know whether the orbits are inclined to our line of sight or not. So those are some limitations. So in the next part of Chapter 15, we'll be talking about patterns that we see. Now that we can measure all these things about stars, we put all this information together and we start to see some patterns developing, some things about stars that we can start to maybe then understand how they're created, how they live their lives, and how they die.